Hello, welcome back. For this video, we will be evaluating the integral of cosecant squared x plus ln of sine x all over cotangent x plus ln of sine x. The integral evaluated from pi over 4 to pi over 3. I suggest that you try this first on your own before looking at my solution. And if you're ready, let's go. For this integral, note that the denominator has a cotangent x, and then the denominator has cosecant squared x. Remember that the derivative of cotangent x is negative cosecant squared x. So it's possible, maybe, just maybe, that if we let u be something like the denominator, we will get something like uh, the numerator in a way or so. So before you explore other solutions, you first try to make a u substitution involving the denominator. And to do that, we first look at the derivative of cotangent x plus ln of sine x. The derivative of cotangent x is negative cosecant squared, while that of ln of sine x, using the product rule, is 1 over, sorry, chain rule is 1 over sine x times cosine x, which is equivalent to cotangent of x. Oops, I think I missed an x here. Now, now this cosecant squared x here is present already in the numerator, so what we can do is we can just introduce a cotangent x in the numerator so that we'll have something like the derivative that we want. And that's what we'll do. We will add and subtract cotangent x to the numerator. If we do that, we can split the integral into two. So the first part involves cosecant squared x minus cotangent x in the numerator, while the other one involves cotangent x plus ln of sine x. Now, why is this good? Because the first one, the numerator of the first one, is the derivative of the denominator. So we can let u, for the first one, we can let u equals the denominator, and then the resulting numerator is just the negative of du. That's why we have a negative here and du here. So it's du over u. So I don't want to evaluate yet or change yet the bounds of integration. So let's just label them u1 and u2 for now. On the other hand, the second integral right here, the integrand simplifies to just 1. So this just becomes the integral of dx from pi over 4 to pi over 3. Now, both of these new integrals are quite easy to evaluate. The first one is just ln of u. Actually, it's the absolute value of u. But for notation purposes, let's just say it's just u. And then the second term is just pi over 3, the upper bound, minus the lower bound, because it's um, a constant value. Okay, and then if we apply the properties of logarithm, this one becomes ln of u sub 1 over u sub 2. So this is effectively just using properties of logarithms. Okay, we have the u2, then u1 here, and then the negative sign outside, and then becomes u sub 1 over u sub 2. I hope that's clear. And finally, we just substitute back u1, which is equivalent to cotangent x plus ln of sine x evaluated at x equals pi over 4. So this is the pi over 4. And then u sub 2 is the same expression evaluated at pi over 3. So that's why we get here cotangent pi over 3 plus ln of sine of pi over 3. Now it's just algebra, trigonometry at this point. We will just have to evaluate these values. Cotangent pi over 4 is 1. Sine pi over 4 is square root of 2 over 2. Cotangent pi over 3 is square root of 3 over 3. And then sine pi over 3 is square root of 3 over 2. So this is the entire expression right here. And then we still have the plus pi over 12. Now this cannot be simplified further, at least not in any meaningful way. So it's probably good to just leave it this way. You might want to approximate this using your calculator to get 0.6721. So this is our final answer. So the key trick here, what we did is we just add and subtract the cotangent x. And we got this idea by looking at the derivative of cotangent x plus ln of sine x. All right. Okay, if you have any questions, clarifications, or violent reactions, just let me know in the comments. Okay, see you on the next one, and bye bye.